Okay, there's one more thing that I want to talk about to finish up talking about the statistical weight. And now I want to go back to the example of dice throws. In this case, I want to consider 4 consecutive dice throws. And so here's the question that I want to ask. Now, by the way, I know that the top, or I now realize the top is really blurry, or not blurry, but very bright because the lights are now a lot more than what they were before. So I will try to be cognizant of that, but hopefully you'll still be able to make out what I'm writing. Here's what I want to think about. I would like to know, so we're going to consider 4 6-sided dice throws. And here's the question that I want to answer. What is the probability that I get the following? 2 of, let me write, 2 times face 3, 1 times face 4, 1 times face 6. What is the probability that after I throw a 6-sided die 4 times, that I get the following outcome? Twice I observe face 3, 1 time I observe face 4, 1 time I observe face 6. Now what I've written here might not be obvious, but what this is a distribution. Not a probability distribution, but a distribution of objects among different categories. The objects that we're distributing are 4 in number, the 4 distinguishable die tosses. The distribution among the bins, the distribution or the sorting of objects among the categories, in this case category face 1, category face 2, category face 3, and so on, is as follows. If n1 is number of times face 1 is observed, and n2 is the number of times that face 2 is observed in a sequence of 4 consecutive dice throws, and so on and so on through n6 and sub 6. This is a distribution. The distribution of our die tosses or dice throws that we're interested in is as follows. If we write this down, n1, n2, n3, n4, n5, n6. Underneath it, we will write the total number of times a given face was observed in the distribution of our interest. n1 is 0. n2 is 0. n3, face number 3, is 2. Face number 3, we want to know what the probability is observing it twice out of the 4 die tosses. n4 is 1. n5 is 0. n6 is 1. This is the distribution that we're interested in. We have to specify the distribution that we want as one of the kind of rational questions that we could ask about the 4 consecutive dice throws. So we want the probability that this distribution is obtained. That's the probability that we want. This probability should look like this. The probability that we're interested in should look like some number that counts all the different ways the distribution could be achieved. For example, coin toss number 1, you get face 3. Coin toss number 2, not coin toss. Die toss number 1, you get face 3. Die toss number 2, you get face 4. Die toss number 3, you get face 6. Die toss number 4, you get face 3 again. Another distribution might be, or I'm sorry, another outcome consistent with this distribution might be face number 3 on toss 1, face number 3 on toss 2, face number 4 on toss 3, face number 6 on toss 4. So the distribution that we've specified for which we want the probability can be achieved in a number of different ways. What is the probability consistent with all those ways that counts all those mutually exclusive outcomes that are consistent with this distribution? We know that it's going to look like some omega, some statistical weight, some number that counts all of those outcomes at once, consistent with this distribution, times the probability of any one of those outcomes. What's the probability of any one of the outcomes of a sequence of 4 dice tosses? We know that the probability of getting any face on die 1 is 1/6. The probability of getting any face on die toss 2 is also 1/6. They're unaffected. They're independent. They're uncorrelated. The probability to get any face for toss 3 is also 1/6. The probability to get face 4 is also 1/6. The total probability for any specific outcome is 1/6 to the 4th power. Just like before with coins, this was 1/2. Now it's 1/6 to the 4th power. But we need the omega for this distribution. This omega looks like before. In the numerator goes the total number of objects factorial. The objects we have in mind are the 4 distinguishable dice throws. 4 factorial. Now, the distribution should look like this. In the first category, face 1, I have nothing, according to the distribution that I'm interested in. So we get 0 factorial. In the second bin or category, I have nothing. I again put down 0 factorial. In the third category, I have 2 objects, 2 factorial. Fourth category, I have 1 object, 1 factorial. Fifth category, I have 0 objects, 0 factorial. Sixth category, I have 1 object, 6th factorial. 1 factorial. You can see that 4 factorial is 4 times 3 times 2 times 1. This is 2 times 1. So the 2 will cancel the 2. That will leave 4 times 3 in the numerator. And so this probability is equal to 12 times 1/6 to the 4th power. That is to say, there are 12 mutually distinguishable outcomes, mutually exclusive outcomes, for which that are consistent with this distribution. Each one of these 12 different outcomes will have a face 3, a face 4, and a face 6 occurring in different places among the 4 dice throws, with face 3 occurring twice, face 4 occurring once, face 6 occurring once. So there'll be 12 of them, and for this case, if you really wanted to, you could list them, but I don't know if I recommend it for your blood pressure. And so that's how we would find this. And so this is the probability that upon 4 consecutive coin tosses, you obtain this specific distribution. That's the probability. Now what I want to do is rephrase this question a little bit differently and ask and arrive at a similar answer, but the reasoning that we will use to arrive at that similar, same answer will be a little bit different, and it will be useful as we go forward. So here's what I want to do. I want to erase and write the following down. Suppose I rephrase my question, or just slightly, and say the following. Now, I know that when I throw a die 4 consecutive times, many different possible distributions could result in principle. For example, I could have 4 each coin toss, giving me a face 1. So I would have N1 with 4 and zeros everywhere else. Another distribution might be 2 6s, 1, 5, 1, 2. Or 1, 2, 1, 3, 1, 4, 1, 5. Or all 4 face 5s. All of these are legitimate distributions that could in principle take place when you throw 4 dice in a row. We may wonder, what is the probability, or this is how we're going to rephrase the question. Given that there are many possible distributions that could happen, what is the probability of this specific distribution? Given that many could happen. And the way we're going to reason is as follows. There's a certain number of ways of achieving this specific distribution. This specific distribution. If we want the probability of this specific distribution, we should divide it by the total number of ways of obtaining all possible outcomes. That is to say, there is some number of ways of obtaining this distribution. That number of ways of obtaining the distribution in 4 die throws is this omega. But there will be other distributions, each with their own omega. And the total number of outcomes of all possible outcomes, independent of distribution, is the sum of the number of outcomes for each unique distribution. That is to say, if you wanted to know how many all possible outcomes are there, not just for this distribution, but for all possible distributions, you would, in principle, write down all possible distributions that are consistent with 4 die tosses. Just like we just said. For example, one distribution will be all 4 gave you face 1. Another distribution will be all 4 gave you face 2. Another distribution will be, 2 face 3s, 2 face 4s. You would write down all of them. You would calculate the omega for all of them. You would add up all those omegas for all those distributions. And that's the total number of all possible outcomes. But we want to know the probability of this specific occurrence, of this specific distribution. Let's call this distribution omega naught. So what we can also say is the probability of obtaining distribution, division among bins, distribution omega naught relative, we'll put this in parentheses, relative to all possible outcomes, right? Possible outcomes. That probability is the total number of ways this distribution can be achieved. Actually, I shouldn't say this. Distribution, let's just call this distribution 0. This is our distribution of interest. I shouldn't confuse the idea of the concept of the distribution, shouldn't confuse that with the number of ways of achieving that distribution, the number of outcomes that give rise to that distribution. That's omega. This is the label of the distribution. We called it 0. Our distribution of interest. And over here, I should in fact just label it as distribution naught. Looks like a face. Distribution naught. This is our distribution of interest. What is the probability of achieving this distribution? It is the number of ways in which this distribution could be achieved, omega naught, this quantity. Let's put a little naught here. Relative to all the possible ways of achieving all other distributions. There will be many distributions. We can label them 1, 2, 3, 4, 5, 6, whatever. Sum on, let's say, I equals 1 to some number little n of omega sub I. I probably shouldn't use little n since we used it above. Let me use big N. Big N. Where big N is total number of distributions for 4 dice tosses. So the probability that we obtain here, or the probability of obtaining this distribution out of all possible distributions, is the number of ways of achieving this distribution, omega naught, divided by all the possible ways of achieving all other distributions. And that'll be the total number of outcomes. So we identify distribution 1, we calculate its omega in exactly the same way, whatever the distribution might be, and you should convince yourself that you can do this for different distributions. Now we go to omega 2, whatever some other distribution. You calculate omega for it, add it to the first one, then do this for the third and the fourth and the fifth and the sixth distribution, all the ones consistent with 4 dice throws. Clearly, the fewer dice throws there are, the fewer distributions there will be consistent with that number of dice throws. Whereas the more dice throws you have, the more distributions will be consistent with that number of outcomes. Or the more ways there are of distributing more outcomes. Now, incidentally, this number in the denominator is again the total number of all possible outcomes. All possible So the denominator is the total number of all possible outcomes for all the distributions. And so we talked about the fact that to obtain this number, you have to list, in principle, all the distributions, write them down, calculate their omegas, add all up all of these omegas for all the distributions, and that's the denominator, and that's the total number of all possible outcomes. But we've also seen another way of obtaining the total number of all possible outcomes kind of from the get-go without doing this. We did this for coins. We can do this for dice. Remember, the reasoning goes as follows. When I throw the first die, I have 6 possible choices, not choices, 6 possible outcomes. When I throw the second die, I have 6 possible outcomes. When I throw the third die, I have 6 possible outcomes. When I throw the fourth die, I have 6 possible outcomes. Therefore, the total number of outcomes should also be 6 to the 4th. So what this formula looks like is omega naught, the statistical weight for our distribution of interest, divided by 6 to the 4th, where this is the total number of outcomes. But check this out. Omega naught divided by 6 to the 4th, same as multiplying by 1/6 to the 4th. So the two answers are actually identical. But the reasoning that we apply is a little bit different. Not a lot, but a little bit different. And it's worth noting the two. And so the reason I wanted to do this, even though we end up with the exact same outcome, is that we will soon be calculating probabilities of specific distributions. For example, the probability of this specific distribution that we called naught, distribution naught, can be achieved in omega naught ways. This is it. Divided by the total number of outcomes gives the probability of that specific distribution. And so that's the kind of reasoning that we will shortly use.